Hi, this is my second video on the Michelson and Morley experiments in 1881 and 1887, and this is the Rant version. You cannot watch this unless you've seen the praise version before. So if you haven't had a look at that video, please go to the praise one. But this is the Rant one. I've got sugar in my body and I'm going as fast as light. I'm assuming you know all about the experiment already, so here we go. Let's see. The praise video, again, you know, you can watch on my channel, and this is the rant video. And I'm not going to rant about the experiment because it's beautiful and it had a profound impact on the development of physics. It's one of the most famous experiments in physics. But the way Michelson and Morley wrote their papers, you know, to me, it's like, I'm going to rant, I'm going to rant. You know, there's things, you know, there's assumptions just dropping out of the sky. There are errors in there. Well, the first one has been acknowledged. You can even read about it on Wikipedia, but I think there's another one. I know this is a big statement, but you know, I'm going for it. I'm going to add clarity and rigor. I'm going to state that the graph of the results is wrong. The theoretical results is wrong. I'm going to map the numerical results to the actual graphical results, which no one is doing, but you know, they're not the same. We need a solution for this. We are going to see how I think the final graph should have looked like. And there's lots of mathematics involved, and it just also drops from the sky without any explanation. And I had a hard time filling in all these gaps, but I will add them in this video. So why do I think this video is different on this experiment? Well, A, no one is ranting. It's one of a kind. It's filling in the blanks, adding clarity and rigor, and I'm going to pinpoint 2 errors in the paper which I believe are truly there. Here we go. Fasten your seatbelts. So let's have a race. I'm going to repeat just a little bit from the praise video to get you warmed up. Here we have the experiment. We have the ether rushing by with 30,000 meters per second. And we have 2 light rays, B and C, and they are going to do a race against each other. B is going against and with the ether, and we can calculate the speeds using the equations from the praise video. And I'm going to ask ray number C to do the same as well, and this ray will be perpendicular to the ether wind, and we can calculate these velocities as well. These were the equations, you should know them, and it's just old-fashioned Galilean relativity with some Pythagorean theorem stuff also going on. And if you then calculate who wins the race of these 2 light waves, then C wins by 0.2 lambda, lambda being the wavelength, if you assume that the light that was used has a wavelength of 550 nanometers. Warming up. Next, we're going to put the experiment 90 degrees, and then we're going to repeat the race again. And here you will see that now B wins. We have the same velocities, but they switch from B to C and C to B. And then we have this, and that means that now B wins by 0.2 wavelengths. And now you can combine the two. In race 1, B wins. C wins. In race 2, B wins, and if you put it all together, then the difference between the 2 races is 0.4 lambda. And yes, it was in the paper. Let me make myself small. So here you can see. And you know, I introduced a new symbol. Well, not really a symbol. I introduced the label delta delta L because it's quite different when you compare 2 races versus comparing the single race, you know, which is delta L. And this got me really confused, and that's why I'm ranting, and I will also rant about the lambda. So Are you ready? 10 rants. Here we go. Rant number 1. The paper says the Earth, planet Earth, is going at 30,000 meters per second relative to the ether. Why? It's not explained, it's just a statement. Well, the only thing that I could come up with, if we take the sun and we plot in planet Earth, and the Earth goes around the sun, and we know roughly the distance between the sun and the Earth, and we know that the Earth takes about 365 days to make the full circle, we can calculate the speed. So this is what they did. But and I'm not complaining about the lack of explaining this calculation. I'm ranting about the fact that they didn't put in their assumption. Why would the ether be stationary to the sun? Why, And yes, in the original article, in the appendix, in the addendum, they say, well, maybe we should also put in the motion of the solar system itself, etc., etc. But, do it in the beginning, people. Rant number 2. Well, it's not really a rant. I'm just repeating a well-known error in 1881, which is that Michelson, when he graduated at the US Navy, he figured out that the light wave that goes perpendicular to the ether had to take its time. TC is the time it takes the light wave to go up and down in the rays to be this equation. And this is wrong. He forgot to apply the Pythagorean theorem. And then he calculated the delta t to see who wins. And this is what he got. And the 2 is wrong. And you can find this on Wikipedia. It's wrong. The correct equation is the one in 1887. And if you then do delta t, you see they're off by a factor of 2. Warming up, not really a rant, just rephrasing that errors it's prone to errors. And here you see a snapshot from the actual paper. Okay. Now there's a lot of mathematics is also missing. Here you see the equations for the time it takes B to race. Now you see river and you see shore. Why? Because in my praise video, before we went talking about the ether and light waves, I talked about a river being the ether and swimmers having a race against each other being the light waves. So when you see river, just think ether, and when you see swimmer, just think the speed of light. And this was the equation. But then they said this one and they subtracted the 2 and they got this equation. But how do we go from the first part to the second part? They didn't add it to the thing. So here it is. It says, well, I mean, this is just the case, So I am going to fill in the blanks for you. Here we go. There you go. And now you know. Okay. The second error in 1881. This is an error that I could not validate. I looked everywhere. I've read, I think, all papers on the papers. So my claim to fame here, we need rigor. We need clarity. So I'm going to put up a snapshot from the article in 1881. And here we say that they expected a delta L of 4/100. And if you also calculate the wavelength of the yellow light, they say 1200 millimeters is about 2 million wavelengths, then the wavelength has to be 600 nanometers, right? And if you then put that in the equation, the wrong equation, the 1881 equation, you will get 4/100. Okay, so in a single race, C wins and B loses by 0.4 wavelength. Then they say, okay, we can put the whole setup 90 degrees, and now the other ray will win. So if you compare two races, you have to multiply by 2. And so far so good. I'm on the page. And then this happens in 8081. They again multiply this stuff by 2 and saying it will be 0.16. What are we doing here? Delta, delta, delta L, I am completely clueless, and I challenge every professional to either set me in my place or acknowledge that this is really an untold error in the 81 paper. Let's see what happens. Rant number 4. It's totally not clear what they are measuring, and it has to do with the delta L and the delta delta L. So here you see the 87 paper, formulas for delta L. Yeah, I'm on that page, formulas on delta delta L, comparing two races. Yeah, I'm fine. And here you can see it. But what are they doing, I mean, you can have your setup fixed in a fixed position and measure a single race, then mark down the interference pattern, and then swap it 90 degrees, and then mark down the interference pattern again, and then the difference should be at best 0.4 lambda, but you have to assume that the horizontal light wave was aligned with the ether in the first experiment and perpendicular to it in the second experiment. But if you look at the results, it looks like they are plotting delta L values and not delta delta L values, which makes perfect sense. I will come back to this later. So this is delta L versus delta delta L. I mean, this is what they write. You can just read it, I'm just putting it out here. And if you follow these sentences, you can only think of, okay, the setup was slowly moving. They didn't stop. It was going around each time in 6 minutes. And then they did this 6 times. And then they did this experiment on 6 different days. Well, 3 different days, but one in the morning or one at noon and one at PM. And then it just hit me. 6, 6, 6. Maybe this article was not written by Michelson and Morley, and that's why I struggled so much. It's written by someone who loves 666. Then they go on about the micrometer. There are 2 micrometers. The one is the precision mirror, and the other one is apparently some micrometer inside the interferometer. Okay, and then okay, it made sense to me, but it took quite some time to know when they are talking about the first micrometer and the second one. But they also refer to the width of the fringes. Okay, here are the fringes of interfering white light. I challenge you to ask 10 different people, what is the width of a fringe? I'm pretty sure we will get at least 2, maybe 3 different answers. Some of them will measure the actual width of one of the colored stripes. Some will measure the distance between colored stripes, and others will go from hard line to hard line. And I believe Michelson and Morley did the latter, but they didn't tell us. No. So if they wrote it down like this, it would be clear for the reader. Please be gentle to the reader. Now, rant number 5. What is D, the distance from the beam splitter to the mirror, and what is the wavelength of the light actually used? This is 8081. And here it says, we have a clue, D is, 1200. Okay, way. And we have yellow light. Well, yellow light is not very specific, right? There's lots of shades of yellow. But anyways, 2 million, so I can do the math, So I expect the light to have a wavelength of 600. In the same article, The arms are around 1,000 millimeters, and that corresponds to 1.7 million wavelengths. I do the math, different wavelength. Again, I assume this is the sodium light because they used sodium lights in those days. And sodium has a well-known wavelength, which is, well, I would say pretty close. But it's not clear, it's not clear. So in 1887, you might have think, after 6 years we'll do better. No, they come up with this one. This is the micrometer that changes one of the mirrors to get the distance for ray number 1 and ray number 2 as close as they can get. And here they say it's 1 thread, 100 threads, it's 1 inch, and that changes the path with 1,000 wavelengths. I had to think really hard about this, but filling in the blanks. So 1 turn is 0.0254 meters. This is an inch in meters divided by 100. And that's not the change of the path. The path is going from the splitter to the mirror and from the mirror back to the splitter. D is half of the path. So delta D is changed. So that means that delta L is changed by 50% with 1 turn. And that's not 1,000 wavelengths, but 500. And when we do the math, we will get 508 nanometers. Okay, so I guessed it was the average wavelength of the white light used. Same article, we get this one, yellow light, and now we're back at 550. It's just not consistent, people. Moving on. My biggest statement. The article is talking about a race where one of the 2 light rays is aligned with the ether and the other one is perpendicular to the ether. But what happens if you move the setup, which they did, and you have the ether coming in at an angle? Well, they said, in the article, then we expect to measure these fringe shifts. And there it is. No equation, no explanation, only a dotted graph. And they give us another hint. They say, well, this graph has been scaled down by a factor of 8. And then I had to think really, really hard. And then I said, okay, I can reproduce this if I divide the expected delta L, which is the comparison between 2 races, and compare this or divide this by 8, then I get the 0.05. But all the other measurements in the article, they scream single race observations, not the difference between 2 races 90 degrees apart. So I believe that they should have made the graph delta L over 8, and if you scale that down, you get 0.025 lambda. Also, maybe just put in an x-axis and label it, it's a scientific paper, right? We need rigor, people. Maybe also label the y-axis so I know if you are talking single race values or double race values. Also, the equation itself is not there. So, this could go right, this could go terribly wrong for me, but I'm not letting go. So here we have alpha, and I could not find the equation for this situation anywhere. So I had to do it myself. Are you ready for it? I believe the equation for the expected theoretical results to be this one. Yes, no, I did not do this in one afternoon. It took me quite some time. But when I plotted it, I noticed, it looks a bit like this. And then I did the actual calculations. It's exactly like this. So it's a cosine to alpha. And if you do the delta L, you turn the table 90 degrees and you exactly get the same expression, but then with a factor of 2. Makes perfect sense. It's consistent. So I went with this to an actual professor in physics teaching the Michelson and Morley experiment to his students in many different classes. And and he plotted the theoretical thingy the same as in the article and said, no. This has to be wrong because of such and such and such and so. And well, he he was, I'm not sure if he was diplomatic or kind. He said, Tom, interesting. All the stuff you're saying makes perfectly sense. I have to go back to the article and see what's going on here. Yes, I believe we all should go back to the article and see what's going on here. It will not change the readings of the experiment. It will change the theoretical expected curve. I believe it should have been like this. Properly label your axis. Now, instead of the angle alpha, I put in the marker positions. There were 16 of them. Just say, you're doing single race displacement delta L, and then it's not delta delta L divided by 8, but delta L divided by 8. But delta L was 0.2, which we saw in the brace video. But this is the actual graph that Michelson and Morley put in their paper. Scaled, Y, not labeled, and I believe wrong by a factor of 2. Again, a factor of 2. Okay, next rant, there are numerical results in the paper. So I thought, let's have a look at them and see what they are all about. Boy, oh boy, oh boy, was I in for a treat. So I'm going to open the curtain because this will take us a little bit longer to fully understand this table. So break it down. I'll start with the top. These are the 16 markers on the setup, and they were able to turn their setup 20.5 degrees, I believe, every time, because then you go round in 16 steps. They don't tell us, but, let's assume this is the case. Then I was wondering, why do they start with 16 and not with 1? I don't know. I did not find the answer. What was the alignment of setup 16? Was the ether perpendicular to ray number B, or perpendicular to ray number C, or something else? I have no clue. So I started thinking, and this is my statement. I think the ether is coming in at 45 degrees, and we would expect no delta L. Both light rays are struggling with the ether the same way, and they will reach the finish line at the same time. You can then, if you go to position 2, for instance, it will look like this, where C clearly wins, and this is just an example, I would believe, setup number 4. So what are these numbers in the table? It says the following table gives the means of 6 readings. So let's look at it. Setup 16, it reads 44.7. 44.7 what? And then I thought, it's the divisions, they are looking through the interferometer. They have all these cross wires on the paper, and they see that the central fringe is at the position 44.7, which is strange, right? You begin with an experiment, so you would expect that experiment number 1 would be your baseline measurement, and you would always calibrate the things that it should have been 0, right? But no, it's 44.7. So this is what fringe shifts look like when you use white light, which is a combination of different lights. And I believe they were looking through the glass. This is 50 divisions. And then they saw this. Apparently there's some mystery baseline in the middle. And then they saw the middle of the black fringe for 4.7 divisions away from the baseline. Okay, I'll go along, Then let's see at the other rows. They did this on July 8th, 9, 11, and at noon or at PM, they did it in the 12th. So this makes me wonder, what did Michelson and Morley do on the evening of July 11th in 1887? If someone knows, please tell me. I'm curious, because they decided not to do any measurements and wait for the next evening to put in the PM values. Then they take the mean. Well, I'm not trusting anyone, so I did some checking and fact checking here. But yes, the mean seems to be right. And then they add this line, the mean in WL. What's WL? Well, okay, wavelengths, but it took me some time. And the wavelength, well, what is the wavelength? When we are doing white light, there's no single wavelength. But again, if you take the number 550 nanometers, which is just one of the options in the article, you will get these. You divide and then, well, you get the wavelength position. So if the fringe shifts 50 division markers, then that's one wavelength, and that's how you get to these means. Divide by 50. Okay, cool. Next, what's this? New numbers, not labeled. Well, if you look closely, these numbers are taken from the readings 8 to 16. And if you turn the table, you will see that setup 8 is, well, it's not the same as setup 16, but the outcome, the expected result, should be the same. So they took the measurements of 8 and 16 and just put them beneath the ones in front. It's when you rotate the table 180 degrees. Here you see it. If you compare setup 2 with setup 10, it's not the same, but in both cases, C will win by 0.2 lambda. And that's what they did. That's the final mean in here. Okay, now we understand the table. Rant number 9. Let's see how the numerical values correspond to the graph. Are you ready for this? These are the final means, right? And this is the picture they put in the article. Noon, PM. I took them out and scaled them a little bit, but these are the actual measurements. This is when I plot the noon values. So how did they go from the table to the graph? And the same for PM. And it was really difficult to solve this mystery, but I had to solve it. So what I did is I searched online and I found a paper in 1933, many years after. It's a paper by Miller, and he's doing stuff, Michelson and Morley stuff together with Morley, and then Morley tells him that when they experience a drift in their data, they compensate for this drift in a specific way. You can read it yourself, and I believe that it will be, where is my cursor? I believe that will be this equation. So they want to have the first and the last measurement to be exactly the same. The first and the last, they want to correct for this drift, and they do so in this matter. And I made an animation. So let's see if that works. So yeah, so this is step number 1, getting rid of the drift. But it's nowhere near the 0 line. So let's assume that there's a constant bias. So we're going to drop it down, drop it like it's hot. And there it goes. Still, it's not the same. Well, let's flip it over. So I'm flipping it over. I don't know why. This could be a convention about directions, which is positive, which is negative. But why would you change that convention between the table and the graph? But if you now slide it in, I think this is what they did. And if you want to do the calculations yourself, these are my actual numbers using the equation I just showed you. Let's do it for PM, exactly the same. So first, getting rid of the drift. Second, drop it like it's hot. Third, flip it. And fourth, slide it over. And yeah. I think this is what they did. And here are my numbers. But you know, how can you just skip this when you are writing this scientific paper? I don't know. So we're almost at the end. I'm going to add a few animations about the missing math. This is a slide from the praise video, so I'm not going over it again, but you see different steps and simplification. So here we go. The first one is this one in the 87 paper, time B. You will see here river and you will see shore, but again, as I told you before, river is ether and B and C are swimmers or light rays. This was the equation and they went from this to this. How do you do this? Well, this is not that difficult, but let's see it in action. Here's it in the actual paper. Here we go. Okay, now you know. Moving on. Number 2, time C goes from this to this. How? Why? Please explain. You know what they did? They just drop it on you and they say it's evidently, etc., etc. No, it's not evidently. Let's have a look. And now you know. Okay, another one. This one we already did, but now they simplify it to this. Say what? It's neglecting terms of the fourth order. That's all we have to go on. Well, in this case, there's something called the Maclaurin series, which says if you have the function 1 divided by 1 minus x, you can approximate this by 1 plus x, if x is really small. And that's what they did. You see here in the animation. Now you know. Next, we're almost there. We're really almost there. Simplifying this into this. Say what? And here it is on paper. Well, this is the binomial series, which says you can approximate the square root of 1 plus x by 1 over x divided by 2 if x is really, really small. Well, this doesn't need any animation. You can just straight see it from the get-go, I would say. This is it, people. We're there. We're there. I want to thank you for your patience and please go watch the praise video if you haven't done so. See you next time. Bye-bye.